Alright, here we go. We're going to take a nice calm approach to this problem. And I kind of just have an idea of what I want to do, but this is going to be real time. You know what I mean? So we're looking at this thing. And hey, it's bounded. You know what I mean? Well, what does it do? Well, let's just take this paddle, and I'm just going to draw a circle because we're doing circle mechanics. And hey, that's point O. And it looks like we have something like at a 45. You know what I mean? And this thing, they say, is spinning. Okay, so this thing can just be like anywhere, right? For this problem, this thing is spinning at a constant speed. So if we start a drill, you know what I mean? If we have a drill gun, and it's spinning, guess what? It's spinning at a constant speed. You know what I mean? Let's just say it's 1,000 RPM. You know, 1,000 RPM. Let's say it's 6,000 RPM. You know what I mean? Whoa. That's a big drill. But even how many rounds a second is that? Well, there's 60 seconds in a minute. I mean, you got to divide by 60. You can figure that one out on your own. But yeah, we take 6 goes to 1, take away a 0. Hey, this is 100 rounds per minute. Okay, well, let's say it was just 1,000 RPMs. You know, let's go back to 1,000 RPMs. How many, you know, if 6,000 RPMs was 100, well, how many is just 1,000? We'd have to divide by 6. You know what I mean? Let's just say divide by 10. Well, that's 100 divided by 10. That's about 10. There's a little more. So let's say it's just 15. 15 rounds per second. Oh, so even my drill going at 1,000 RPMs, it's only going around 15 times a second. Hey, that's a number I can deal with. So 15 revolutions per second. Okay, so anytime you're dealing with circles, we got to know something about circles. So we got that aspect. But now check this out. Check this out because like this is pretty wild because it's saying, and it's measuring the angle from here. You know what I mean? This is like 45 degrees or whatever. But it's saying, hey, look at this. Look at this. We have a little box. You know what I mean? We box this in. And right there. And so this thing's spinning, but guess what? You know what I mean? It's gonna get to here, and what's gonna happen? Like, cause you got a little slider in there. Well, this little slider's gonna be like, nope, stop. It's going to stop right there. So, like, literally, that's as far as it can go that way. And the same thing over here. This thing can go only... So, even if it started right in the middle, and then you're just like, okay, now we're going to go at a constant speed this way. Well, look, it ain't going for very long. So, even this problem is a one and done. I don't even know if this is an invention. I don't even know what this does. Maybe it goes to here and then it like slams. You know what I mean? It like slams into the ground. So, you know, so see how you have this casing here? Well, let's say that casing is open. So, and then our slider pops out and then it hammers past that surface. You know what I mean? That makes more sense to me. And it explains why you'd even have this thing. But even though it's saying this is a constant at... in the problem it says it's going 10 radians per second. I'm just going to give it to you. 6.28 radians is equal to 1 revolution. And even simpler, 6 radians is equal to 1 revolution. So isn't this close to... This is just close to 12. So let's just say it's 12 and get on with life. And let's say this is... so every second it's going around twice. Okay, so it's going around 2 revolutions per second. This will probably be a little bit easier to understand. Okay, so if it's going around 2 revolutions in 1 second, well, how many... Let's say it's just half a second. Well, it went 1 revolution. Okay, how about 0.25 seconds? A quarter of a second. Well, it went half a revolution. Okay, well, even right here, that's the crazy thing. Like, it should just be jumping out at you that this thing can't even rotate halfway. Like if I don't want to draw in my book, but look at that. That's a 90-degree angle. So let's just do one more. In an eighth of a second. In an eighth of, that's 0.125 seconds. And we're just guesstimating, you know what I mean? This thing's going a quarter of a revolution. Alright, so yeah, in the speed they say this thing is moving, just in an eighth of a second, you know what I mean? Like, if I had a stopwatch and went click, click, hey, 0.125 would probably show up. Actually, you'd probably do it faster. You'd be like, click, 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 click. That's probably eighth of a second. So, click, click. This thing moved. And look, this is half a meter. Okay, so, see now, even just that, like, you're like, whoa, mind blown. I never even thought I could do a project where, you know, okay, so half a meter, you know, is a meter 3 feet? Sure. For you, a meter's 3 feet. For me, a meter is 40 inches. It's closer to 40 inches than it is 36, that's for sure. So this is 20 inches. And this is probably like, I don't know, 30. Anyway, who cares? This is like 2 feet. So it goes 2 feet. It goes from here to here. Actually, this is only 45 degrees. So, you know what I mean? In 0.0625 seconds. A 16th of a second. Click, click. Hell yeah. This is going an eighth of a revolution, which is 45 degrees. This is 90 degrees. This is 180 degrees. And this is 360. So even just doing this little chart, I mean, you can stop the movie right now. Mind blown. You're like, oh, I never even thought of taking a problem where it's looking at rotational dynamics and not just going right to secant squared. Going right to tangent theta, derivatizing that, dx dt, but we don't have an x, we got a theta, you know what I mean? So at the end of the day, we're going to get there. dx dt, well, it already says, well, hell yeah, if this is x, you know what I mean? Oh, we all know that x is 0.5, and this is 0.5 meters. We all know that's 0.5 tangent theta. I mean, who doesn't know that this distance to right there is, you know what I mean, is 0.5 tangent theta? If you can't see that, you know, give me a break. So just like we got rotation and we made this little chart, let's do that right now. Because I don't care what the hell the angle is. I don't even care if it's a right angle. You know what I mean? At the end of the day, like, even that might blow your mind, but who cares? Yeah, hopefully it's a right angle. Okay, but here's your angle. What's this length? You know what I mean? Engineers, it took until about sophomore year to be like, whoa, if you don't know this at the drop of a hat, you're going to fail this class. You know what I mean? So it was perfect. One of the engineers teachers was just like, oh my God. Yeah, I get it. From your homework, I know like this part takes you 15 minutes to figure out, and we need you to figure it out in a half of a second. So opposite, so sine, so like, hey, sine, I don't know. Sine, sun, maybe this is a sun, I don't know. You figure it out, but if you, hey, that like no one's done that before. Hey, that's the sun. Hell yeah, and this is the sun theta. You know what I mean? Sine theta. Hell yeah, r sine theta. But anyway, wait. You know what I mean? This is the sine theta part, and this is the cosine theta part. Cosine theta, you know what I mean? I don't know if there's any magical trick, but it's adjacent. I mean, sun, sine, sunshine, it's across, I don't know, on the horizon, anyway. But the cosine theta is just the adjacent part. Adjacent. I don't know. But anyway, those are honestly the only two you need. And then every once in a while, you have to know that tan theta is sine over cosine. And that makes sense. I don't know. We learn sines first and then cosines. This is just straight memory that I know that tangent theta is sine over cosine. I don't know it any other way, and I know a little bit about it. But anyway, the other things, you know, from other videos, if you don't know nothing about nothing, you know, and sine theta or cosine theta, well, for engineering purposes, this is just a number between 0 and 1. You know what I mean? If you're a mathematician, this is a number between -1 and 1, but we're not mathematicians. We're engineers. Who cares about the negative part? There's nothing called negative distance anyway. So anytime you're dealing with sine theta and cosine theta, it's just 0 and 1. But let me blow your mind a little bit farther, and let's just say it's 0% to 100%. 100% of what? Well, of this thing we always called the hypotenuse, you know what I mean? Or the radius, or the hypotenuse, you know what I mean? Whatever you want to call it, this part, let's say this is 30 degrees. Well, guess what? This part is 50% of that part. You know what I mean? If I know this part's 50%. And if this is 30 degrees, this is the only one I know just by memory, is this is 80, oh shoot, it's either 86.6%, and I think that's it, final answer. Cosine, oh, we got to get into degrees. And cosine 30, yeah, oh good, yeah, but it's 86.6%, you know what I mean? Hey, at the end of the day, is this close to 100%? Sure, you know what I mean? You could guess that badly, but it helps you, you know what I mean? Because when you plug in your into your calculator and you're just like, all right, sine of 30, it's going to pop out 0.5. And you'll be like, look at that one. It's shorter. And cosine 30 is going to pop out 0.866. Now, any number less than 1, your brain just gets fried. And you're just like, I don't get it. But if you consider these percents, hey, that's 50%. Hey, this is 86.6%. And these numbers will never be higher than 100%, never be lower than 0%. All right, so that kind of gets us there. Those are the only two. Like, you just need to be like, whoa, I got an angle like this. There's the theta, and I want to know this height. I want to know the height of a person. I don't know, but I'm measuring this height, which is really weird. I don't know. So I measured this height. I'm going to call it the radius. This height was 7 feet. And this degrees was 10 degrees. So, hey, we need the adjacent part. This is the sine, sunshine, in your face part. This is the cosine. So just what's cosine 10? Just type it in. That's the first thing you need. Cosine 10. Hey, that's 0.984. Now, instantly turn it into a percent, just 100. You know what I mean? Move the decimal place, too. Hey, 98.4%. Does this make any sense at all? Hell yeah. This height is 98.4% of whatever I measured here at a ridiculous angle. So this 98%, you know, if we want to use this percent as a real number, on a normal friggin' number, you got to get it back to this. But now we're going to times 7 feet. And times, well, we got to divide by 100, get it back to that normal number, times 7. Hey, we got 6 feet. Damn, that was a bad example. Because, unless I'm at a basketball court, holy Toledo, 0.89, what's 0.89 feet? Well, you go 0.89 divided by 12. 0.89 divided by 12. No. What the hell? You go 0.89 times 12. 0.89 times 12, and you get 10. That's almost 11 inches. 10 and a half. This is 6 feet, 10 and a half inches. Oh, my God. You know what I mean? We're talking NBA, baby. Yeah. Okay, so that's the prerequisites. I'm going to start basically every problem with the prerequisites because you're going to be like, whoa, mind blown. You know, if my engineering professor stopped us in our tracks and be like, my God, if you can't take just whatever friggin' angle, you know what I mean, hopefully this is 90 degrees, and say, hey, there's our theta. Now, I don't know if I did that right. Let's do it a little bit better. All right, there's our angle. You know what I mean? What's this height? Well, hey, this is the sun, sunshine, sine. You know what I mean? Keel and peel it to death. But there you go. This is sine theta. And look at that. This is cosine theta. Threw you for a loop because this cosine theta is a little smaller than that. You know what I mean? 0 to 100% on this thing and 0 to 100% on that thing. The only time that they're the same is if you got a 45 degree angle. And in our problem, yeah, we got a 45 degree angle. But anyway, and this is going to be 70.7%, 70.7% because that's sine 45. That's also cosine 45. and this is your radius or hypotenuse, whatever you call it. And whatever this was that you measured, you know what I mean, you can figure out these parts. Anyway, so I think we destroyed that. And I just got to make sure we're still recording. Hell yeah. Alright, we only got 4 minutes left, and I need to change the battery. So we're going to take a quick pause, but we're going to come back to this problem. We're going to do it. We're going to learn a lot about it. You know what I mean? And you see it's bound, and it only going like a, you know, a quarter of a rotation. We'll get into it. Let me change batteries. Catch you on the flip side. Alright, we're back and ready to attack. Okay, so, yeah, like I said, look at this thing. It can only go 45 degrees. So if this arm started here and it's spinning at 10 radians per second, well, what the hell is 10 radians per second? Well, that's like a one, you know what I mean? It's almost 2 revolutions, and it's only a revolution and to there. But that's about 2 revolutions a second. So 0, 1, 0, 1, 0, 1, 0, 1. You know what I mean? So it's going from there to there in well, it's going 90 degrees in an eighth of a second, and it's going from here to here in a 1/16 of a second. So let's say this thing oscillated back and forth. I mean, it's just doing that, or like this is probably an eighth of a second because well, it's got to go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. You know what I mean? So that would be eight cycles in a second. But anyway, what were we saying? It's going from there to there in an eighth of a second. So it's going there, 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 there. That's 1 second. Alright, yeah, I'll count. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's how fast this is singing. And this is like this is 20 inches right there. This is like a full meter. You know what I mean? Well, it's just another. It is 40. It's a full meter swing. So it's going a full meter one way. Yeah. So you got some weight on this, and like I said, you open it up. Maybe you got a hammer. You know what I mean? Maybe you're just pounding dirt. I don't know what you're doing with it. You know what I mean? But it don't tell you that this is an invention or a machine. It just says it's going one direction, and then what's the velocity there? Well, it looks like it's going to tear itself apart because you know, if this didn't slow down, it's just going to like it's bound. It's going to stop pretty damn fast. So I don't know. Maybe you got like a walnut in there, and it's like crushing walnuts. But see, that was the bizarre thing about this problem. Never does it say it actually goes back and does it again. It just says, and it doesn't even say it says this moves at a constant angular velocity, which is crazy because at some point it ain't moving. And where did it start? You know what I mean? You had to turn on the machine, and okay, I get it. Yeah, between here and here, it got up to its constant speed. And then what? And then it just, ran into this thing, and it broke itself apart. Alright, so kind of a weird problem. That's why this one, we already went over, that this is a quick return mechanism. So this thing's going back and forth. It's going one way, like kind of one way slow, and then when it goes back, it's like, whoop, fast back. You know, or however, yeah. Okay, so what's our goal for this problem? Like, what do we want to know that we don't already know? Well, I think we just did it. I mean, literally, the fact that we already have the parameters set. That it's going 10 radians per second. What the hell is that? That's 2 revolutions in a second. But it can only travel 90 degrees. So go back to our little chart. This whole thing is going to be over in an eighth of a second. You know what I mean? This whole problem, just an eighth of a second. So that's what we're dealing with. And what we want to know is we want to know something about this slider. Does this slider move faster? Does it slow down? Does it... and so that's where we're at. So let's grab a new sheet of paper. We'll use this one for reference. So yeah, you have that circle. You have the 45. And then you have this box. And at a certain point, And they show the box like ending right there. So we're going to do exactly what they got going on. You got your 45. You got your box ending basically at 45 degrees. And then you have this little slider in there. And this is 45 degrees. And it wants to know what the velocity is. And we know this distance from here to here is 0.5 meters. So let's say our starting position was just right here. Here's our slider. Here's our 0.5 meters. And we know it's going... well, all we know... See, the speed is 10 radians per second. So now, you know how we actually figured out what the revolutions were? What the hell is a radian? What the hell is the revolutions? We figured out what angles were and sines are. Well, here's a little crash course. Anytime you see the word radians, go radians times radius. You know what I mean? Gets rid of the word radian. That's the take-home point. You know what I mean? Radians sound confusing. So we're going to go 10 radians per second times our radius, which is this 0.5 meters. So here's kind of our, this is our little circle. But when you get out here, when the slider's out here, this is, hey, our circle's changing. So actually our radius is changing. Yeah, so that's the first indication that, whoa. Well, let's first figure this out. So the first, if we're right here, maybe this is our initial condition. You know what I mean? It starts there. Radians times radius, and this is radians per second, don't matter. If you do radians times radius, well, guess what? Radians goes away, and you're left with 5 meters per second. Like you're actually left with something normal. So anytime you see the word radians, so let's go over here. 45 degrees. Well, what the hell is 45 degrees in radians? This is another one. You know what I mean? No one made it simple. I'm sure there's plenty of ways to make it simple. But I just go back to saying, hey, 360 degrees, hey, that's one revolution. And guess what? 6.28 radians is equal to one circle. You know what I mean? One circle or one revolution. You know what I mean? However you want to know that. And actually just make it simple. 6 radians is equal to 1 revolution. Okay, so don't we have something that's equal? So isn't 360 degrees equals to 6 radians? And how do we just get 1 radian? Well, divide by 6. And then that means you got 60 degrees is equal to 1 radian. Okay, but we don't have 60 degrees. Well, what's 30 degrees now? Make that chart. Well, that's 0.5 radians. And at the end of the day, this is super accurate. What's 15 degrees? Well, that's 0.25 radians. Whoa, I never knew that 0.25 radians was 15 degrees. Never in my life. All right, so we'll stop there. But what's 45 degrees? Well, isn't that halfway between 1 radian and 0.5 radians? Sure. So wait, isn't that just 0.75 radians? You're telling me I went my whole life not knowing what radians were, and now I know that 45 degrees? Well, that's just 0.75 radians. And didn't you say radians times radius is something normal? Sure. So what do we want to know? We want to know this distance right here. Or what do we want to know? What the hell do we want to know? So if this is the angle in radians, and we're doing so 0.75 radians, isn't this our radius? Times radius is just the meters. It's just the length of uh-oh. Damn it. Why am I hung up? Let's say you have 0 radians. Oh. Oh my God. No. Whoa. Yes. At the end of the day, radians times radius is something normal. So velocity is probably the most normal one, because radians per second times radius is the velocity. Is just we're talking Toretto here. How fast my car going around? I'm driving around a circle. I could care less about that. Someone says I'm going radians per second. I don't know. I'm Toretto. You know what I mean? But I do know that if I take that radians per second times radius, I'll know my velocity. You know what I mean? In meters per second, but we're fine with that. But I guess, yeah, if I just have an angle, so we're just saying, hell, I got an angle. Well, you must have a circle, and this is your center. Ugh. And this is your This is your radius. This is also your radius. So and someone said this is 0.75 radians. So what's 0.75 radians times radius? Well, that's going to be this length right here. Okay, so let's go back to our problem. And so this really don't help us. We don't need to know that, hey, this is part of a circle up here, that looks like a big pizza pie. And we don't need to know this length. This length is usually called S. It's your arc length. Yeah. So, but that'll be useful for other problems. You know what I mean? So if we know this length right here, we can go this length, R, times the radians, 0.75 radians, and that'll give us this arc length, or S, arc length. And that'll be from there to there. But unnecessary for this problem, because we just got things sliding on but it would be necessary if this thing wasn't sliding and your slider was up here and it's coming down to hammer something. You know what I mean? Hey, let's say it's just a swing arm, and right here it's like kablamo. How fast is it going? Well, it's going to be going Toretto style velocity, radians per second times radius, and then we get the normal just velocity. You know what I mean? And let's say we measured it. We're just like, well, I don't know. I'm going to measure right here. Here's like so in 1/10 of a second later, it's smashing down. So I want to know its velocity. Well, isn't velocity just meters per second? Isn't that just distance over time? And I know the time. Do I know the distance? Well, hell yeah, because I know this is 0.75 radians, or 45 degrees. And so I know distance, I know this arc length, because that's, you were just saying radians times radius is something normal. Yeah, so I have 0.75, and we need to find out what this radius is. And we'll just say it's the initial radius, 0.5 meters, so 0.5 meters. Well, hell yeah. 0.75 times 0.5. All right. So yeah, you got 0.375 meters per second. So this is the arc length. I guess this is a smaller circle. Kablamo right there. But this 0.5 meters, took 1 second. And this distance is 0.375 meters per second. You know what I mean? That's the speed. But because we're doing this straight line, you know what I mean? Now we got something different. So anyway, so that was just a crash course on radians. Always, anytime you see the word radians, just say radians times radius is, holy crap, something normal. You know what I mean? Now the normalness is an arc length. Okay, that's not too normal, but we can dig. Normalness is velocity. Hell yeah, Toretto style velocity. Or, you know what I mean? Radians per second squared. That's considered alpha. Radians per second is considered omega. Like, are you kidding me? Like you're going alpha and omega style. Like what are we? Is this biblical stuff? But anyway, so this is radians per second, angular speed. So speed. Velocity, if you times by something, radius, get something normal. This is acceleration. If you take angular acceleration times radius, you get something normal. Toretto-style acceleration. Off the line, even though he's going on a quarter circle track, I don't know. But anyway, so again, this whole problem, and I set this up, was to go over these examples of like, okay, the problem said we're let's put a time factor on it. Hey, it said radians per second, and we're doing a circle. How many revolutions is that? Shoot, we're only going 90 degrees before something crazy happens. And then we need to know something about angles. Now we need to go back and know something about radians per second, because radians pops up everywhere. It pops up as arc length, pops up as radians per second. Luckily, this thing don't accelerate, so the spinning is just constant. So it's just going from here to there at a constant speed. Makes no sense because it's got to stop somewhere. Obviously, that would be alpha. Your angular change in angular speed. For sure, this change in angular speed's got to stop at some point. Okay. All right. So now we can use a method to actually solve this problem. And so that might be the most exciting part. Get back here. Here's kind of that first radius is 0.5 meters. But over here at our 45 degree angle mark with our slider banging against something, this is 45 degree. We'll go 0.75 radians, 45 degrees. And what do we want to know? Well, first, this is 45. Okay. So, well, let's just do it. Let's say this is our theta. This is our sunshine. This is the opposite. Doesn't this mean this is sine, sine theta? Yeah, and doesn't this mean this is cosine theta? Hell yeah, hell yeah. But didn't we say that sine theta is equal to, you know what I mean? This radius or the hypotenuse it's the hypotenuse over, you know what I mean? This distance. Or actually, but as engineers, we kind of just know the 0.5 second thing is like, hey, if this is x, this is the distance we want to know, x. X is equal to the radius sine theta. Usually, we always know this, you know what I mean? Where we're given a funny length at an angle, just like we are here, and we want to know what this distance is. Well, we know that this x is this distance r, you know what I mean, r sine theta, or h hypotenuse, hypotenuse sine theta. So in 0.5 seconds, this is what an engineer knows. So we just instantly go right to here. We don't start with like, oh, sine theta is equal to, hypotenuse over, or no, it's not even I even got it wrong anyway. Opposite over hypotenuse, you know what I mean? We just instantly say, hey, we know our theta, so this distance x is equal to r sine theta. This distance x is hypotenuse sine theta, but we usually use r. We could use h though, but that's just the fastest way at the end of the day. But do we know our radius? No, not yet. Not yet. We don't even know it. So that's why this problem uses tangent. Because if we know this degree, so what's tangent? Tangent says, if we got the tangent of our angle, that's equal to sine, that's equal sine theta cosine theta. But that don't help us out. But we also know that tangent theta is equal to, so if this is our sunshine, tangent theta is equal to the opposite over the adjacent. But didn't we say the opposite was sine? Yeah, that's why you can write this out first. Sine over cosine. Yeah, so tangent of x, this is equal to x divided by, what's that? 0.5 meters. And now you can use, alright, we got to throw a new battery in, and we got to throw another 20 minutes on the clock. Alright, so another 20 minutes on the clock. We're almost done with the setup of this problem. Okay, so tangent. So here's our angle. I know it's all scrambled, but it's opposite, this x over 0.5. And then, hey, we can just solve for what the hell this is. X, You know what I mean? X is equal to, hey, take that upstairs. You know what I mean? X is 0.5 meters times tangent of our angle. And yeah. And but what? So here's where you can pop this back in. Well, isn't tangent theta just sine theta over cosine theta? Yeah. So isn't this 0.5 meters sine theta over cosine theta? Sure. And isn't in radians is just 0.5 meters? Well, let's do it in degrees first. Isn't this just sine 45 degrees over cosine 45 degrees? You know where this is? Yeah, and isn't sine 45 degrees the same as cosine 45? Yeah, sine 45 is 0.707. Cosine 45 is equal to 0.707. 007. Kinda. You know, it's kind of 007. But anyway, yeah, so isn't X just 0.5 meters? Yes. Yeah, this is just 0.5. It's 45 degree angle. We all know that. But when this slider thing, you know what I mean, is anywhere, you know what I mean, it's not, like here it's 45 degrees, sure. But it can start out at 0 degrees. It can start out right here. And then what's X? Well, if it starts out right here, X is 0. And if it starts right over here, X is 0.5 meters. Alright, and then it runs into a friggin' wall. So we already know something about something. And honestly, the only thing this asks is, like it asks, find the total velocity of the pin, you know what I mean, using polar and Cartesian. Anyway, it was a simple question of what's the velocity at that point. Well, other problems are going to be like, well, what's the velocity, you know, what's the equation for the velocity of this at any point, you know what I mean? And that's where, if it's just a circle, and you got this arm spinning, and it's spinning around at a constant speed, well, the velocity is constant. It's tread velocity, which we said was radians per second times radius. And then we just get a normal meters per second. And then we're done. But the fact that it's traveling on a straight thing, well, let's look at that. And I think we need to do that. So here's what it is. So now you just want to make a small one and a big one. And I would say make a real big one. You know what I mean? So you're going to be way the heck out here. Here's your initial circle. But guess what? At some point, and this is just going in, the sky's the limit. So at some point, your slider's going to be way the hell out here. And this degree is like, maybe let's say it's 80 degrees. You know what I mean? Oh, whoa, it's way out there. And let's say it's just 70 degrees. Okay, so it's right there. Okay, and now let's go from, this is 0 degrees right there. What's 10 degrees? You know what I mean? This is this slice, so it's got to be about the same. Okay, look at that. So if this thing only moves 10 degrees, hey, it didn't travel very far. So that's what these circle problems are getting at. And this is the way to break it down. And then this last 10 degrees, well, it only moved 10 degrees. It took the same amount of time for this rod to go from here to here. Like, because this rod is spinning around like a drill bit or something, you know what I mean? And so it took like a, you know, same amount of time to go from here to here as it did from here to here. But check it out, the velocity is crazy. You know, in the same amount of time, this thing is like here to there. And in the same amount of time, it's like here to here. Here to here, compared to here to here. You know what I mean? So the velocities increase. And, you know, if you made this way out here, man, 85 degrees, even just a 5 degree difference, I mean, it just goes to infinity. You know what I mean? You can't even make this machine, and it can't even spin once. The most this machine could ever spin is 180 degrees, and then it would have to, like, you know, make its way back or just crash against the end. I don't know what the hell this machine's supposed to do. But this is the best way to look at it. It's like, oh, I never even thought I could just make it real long, and then it actually tells me what the hell's going on. So, at the end of the day, these problems with circles usually want to know velocity and acceleration. Well, we can get velocity because we said, we already did like that first one, where we're just like, yeah, at 10 radians per second, we're doing this. It's about a 45 degree angle, and that's all it can do. Yeah, and we're gonna say it starts all the way over here, else they wouldn't have built it over here. So we're gonna say that, yeah, in 90 degrees it's 0.125 seconds. Okay, perfect. So we already know our time. Time is equal to 0.125 seconds. And what's our distance? What's this distance from here to here? Well, that's 0.5 meters. We already did this. This is a 45-degree angle. So this is 0.5 meters. This is 0.5 meters. So it travels a distance of 1 meter. Okay, so we got a distance of 1 meter. Now this is where you always got, if you're dealing with acceleration and velocity, just like we said, hey, what's revolutions in degrees and seconds? You know, we did that part. But what's the definition of velocity? Well, it's the change in position or divided by change in time. You know, or it's the change in x divided by the change in t. You know what I mean? However you want to do it, but it's like a change in distance or change in distance divided by change in time, which we have distance and time. Perfect. We know velocity then. Let's just plug it in. Velocity is change in distance, 1 meter per 0.125 seconds. And we already said this is 1/8. So we got 1 meter divided by 1/8 of a second. 8 comes upstairs, and guess what? We got 8 meters per second. All right, so this thing's cooking. The velocity of this thing is going real fast. It's going 8 meters a second. And does that check? Because I said if it's in the initial position and it's going 10 radians per second, omega. Radians per second. It's going 10 radians per second. Radians times radius, 0.5 meters. Well, that's 5 meters per second. All right, sweet. All right, so we figured the average. We figured the average velocity was going to be 8 meters per second, just from that initial kind of calculation. And we figured the actual velocity right there is going to be 5 meters per second. And we figured out also from here, let's see if you can see this. So, yeah, we're all in. We figured right here, yeah, that as this thing goes farther this way, it gets faster. So yeah, it doesn't slow down to nothing. You know what I mean? This is kind of just like the slowest speed right here. It's kind of like the average speed. But consider if it's over here, it's like hella faster. It's like, whoa. Or actually, it's real fast, it slows down, and then it speeds back up again. You know, so it's like, so it slows down and then speeds up, and then slows down, you know, and it's just doing it one time. Alright, but now we can do the definition of acceleration, which is the change in velocity divided by the change in time. Well, hey, look at that. We even got two numbers. We said that the velocity at this point was 5 meters per second, and we thought that the velocity in general was 8. You know what I mean? The average velocity is 8. And just given this problem, the velocity at this end point is 10. You know what I mean? And that should make sense theoretically. If the average velocity is 8, so we're like somewhere in the middle, it's 8, and at the slowest it's 5. That means there's got to be points where it's faster. Yes, so even just this. So we have our initial problem. You got 10 meters per second, 10 meters per second, 5 meters per second, and an average velocity of 8 meters per second. So somewhere in here is going to be the average. You know what I mean? Center of mass of the velocity. So anyway, so now, perfect. So now we want to know acceleration. Acceleration is important because F equals ma. Now why would you just say that? My mind just exploded. Well, F equals ma, you know, Newton didn't say F equals mv. You know what I mean? Newton didn't say, hey, if a car's going a certain velocity, it's putting a force on anything. It ain't putting a force on nothing. You know what I mean? It's got potential maybe to like run into a tree. You know what I mean? But guess what? The second it runs into a tree, it ain't going that velocity no more. It's going 0. You know what I mean? 0, not the hero this time. because it ran into a tree. Here's the car. Yeah. But Newton said F equals ma. It says, hey, what you're going to notice is that thing was going fast, and now it ain't going no fast at all, and it happened real fast. So we got acceleration, which is a change in velocity divided by a change in time. Now you can't just say, whoa, I'm going real fast, you know what I mean? Accelerate. Like, even the guy that jumped out of a plane without a parachute, he landed in a big old net, and then he like, whoop-de-doo, he kind of went like all Einstein, you know what I mean? He broke the fabric of time in this net for about 3 seconds. I don't know what the impact was. But yeah, 200 miles an hour, over a period of slowing down of 3 seconds, well, he's alive, you know what I mean? He took those G-forces. His heart didn't stop. But yeah, you hit a tree, well, holy Toledo, it's like 0.01 seconds. A hundredth of a second, clublamo. So acceleration is change in velocity, yes, but if your change in time is real small, guess what? Your force is massive. Massive force. So the only reason in these engineering books they want to know acceleration is like maybe, you don't want the metal just to fly apart. Because we have that video of the saw stop, you know what I mean? Hey, it stopped the saw real good, but the teeth flew off. Now, that didn't harm anyone, but that shows you that acceleration, that deceleration was so powerful. This acceleration was so astronomically large of a number. The mass of the little tooth, even though it was real small, had a force that just ripped it, right out of its, bonding with the surrounding metal. It was amazing. So, yes, F equals ma. So, at the end of the day, you always have to keep that in the back of your mind. If they're asking for velocity, cool. But if they're what we really want to know is acceleration. Newton didn't say F equals mv. He said F equals ma. So, we kind of want to know what the acceleration is. And it's a little bit harder. You're like, well, I don't know. Well, go back to the tree. Go back to that guy that fell into, you know what I mean? It took a long, yeah. So his acceleration, this guy's acceleration is much, much less. Because the time is big. This time goes real big. If it took him 3 days to, soften this net after he fell out of the sky, his acceleration would just be boring. Yawn. But yes, you hit a tree when you're a skier with a car. My God, those things do not move. The time just goes real fast, and acceleration real big. You're the mass. Your force is just crazy, and F equals ma. Okay, so we still need to get a number, though. You still need to get a number on this acceleration, so let's do it. So, yeah, and at the end of the day, their even velocity is 0.5 secant squared theta d theta dt, you know what I mean? Like, my brain is, my brain didn't need that. My brain just wants, hey, let's get a number for A. So that's what we're going to do. And just make sure we got some juice. And I think we can do it in the next 6. Yeah, we got 6 more minutes. So let's do it. It says acceleration is the change in velocity divided by the change in time. This thing moved from here to there, and what did we say the time was? Well, 0.125 seconds. So, and we said, what's our 3 points? Oh, shoot. Yeah, no, this whole thing, from there to there. But we said right here, you know what I mean? It went from 10 to 8 meters per second. And what's that? Well, isn't this like a tenth? Maybe it's just a fifth. We'll just divide it by 5 even. Play it on the safe side. So 0.125. So 0.125 seconds divided by 5. 0.125 divided by 5. Well, that's 0.025 seconds. Now we're getting into small. I don't even know what that is. Anytime you get a small number, just hit your inverse on your calculator. Hey, that's 40. Oh, 1/40th of a second? Okay, I can dig. So it's going to go, so if I go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I count to 40, or if I go back and forth 20 times. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, or like 40, yeah. If I just do this, if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I go to 40, you know, and that was a second. That's how fast it's moved. One of those is just going, yeah, that's the speed. That's the time frame from here to there, okay? Because this is 1/10 of a second. You know, so obviously that's that fast. Okay, we got it. So acceleration, change in velocity, change in time. We know the change in time, 0.025 seconds. Or it's 1/40th of a second. We dig. And what's our change in velocity? Well, 2 meters per second. Okay, 2 meters per second. Okay, yeah, so we don't even use your calculator because we said acceleration, change in velocity of 2 meters per second divided by 1/40th of a second. Well, when you divide by a fraction, the 40 goes upstairs, and you get an acceleration of 80 meters per second squared. Hey, that's a pretty big number. And why? Because you only have 1/40th of a second to slow this down to 8 meters. If you're over here, you only have 1/40th of a second to speed it up from 8 meters to 10 meters per second. And then that's 1 meter per second is about 2 miles an hour, you know, 2 point something. So 2 meters per second is about 5 miles an hour. You know what I mean? So, and you have in a 40th of a second, you're going 5 miles an hour faster. Anyway, acceleration, but we get it. Now we can use this A, and we can say, hey, from there to there, we have an acceleration of 80 meters per second, which is a change in velocity of 80 meters per second every second. So if this is going 0 right here, guess what? It's going like 200 miles an hour in a second, in another second. But we don't have another second. We don't have a full, we got a 40th of a second. So it's only going from 8 meters per second, which is about 20 miles per hour, to 10 meters per second, which is about 25 miles per hour. Like we said, 5 mile an hour difference. And if you want to know that conversion, 10 meters per second, well, just times 2, that'd be 20, plus 25% tip. Well, that's 10% tip is, you know, 10% tip is 1. Another 10% is 1. Plus 5%, that's 0.5. So 2.5. So yeah, it's going to go 22.5. You know, so I was a little bit off. But anyway. Alright, so now that we have our acceleration, we're basically done. And what do we want? What do we want? I think there's one more. I swear my mind is just like, we want to know one more thing. Take a breath. How much time do we got left? We got 2 minutes. Alright, but yes, we did, like even this, it needs secant squared theta radians d theta dt, just to even get the velocity. You have to differentiate this number again to get the acceleration. But at the end of the day, all we want to know is maybe what number is that acceleration. You know what I mean? Because now, oh, that's what I want to do. So we have an acceleration of 80 meters per second, you know, per second. And if F equals ma, oh, anyway, I gotta do one more thing. Okay, so I guess well, let's just say this is a 2 pound, you know, thing. Yeah. Let's just say this is a 2 pound slider, which is 1 kilogram. You know what I mean? And we want to use that F equals ma. Our mass is 1 kilogram. Our acceleration is 80. Our force is going to be 1 times 80, and that's going to be a force of 80 newtons. What's a newton? Well, a newton's a quarter pound. So 80 divided by you know what I mean, 4. Well, that's 20. So we got 20 pounds of force to like push it from there to there to get it to go faster. Alright, so that's using F equals ma. Now, it would be interesting if this thing actually slammed to a stop. It doesn't. You know what I mean? Like, you could put a spring here and say, yeah, this spring is going to slow it down. Or actually, it just rams Earth, and we know that the Earth is going to compress. Let's say the Earth compresses in 100th of a second. So it's going to go from is going to go 10 meters per second to 0 meters per second. It's going to change its velocity by 10 meters per second in a hundredth of a second. Alright, so now we know our acceleration is change in velocity over change in t, which is 10. It changes velocity, it stopped, and it stopped divided by 100. A hundredth of a second, so that's 10 times 100, which is 1,000. So now we can get an acceleration of 1,000. So now we can say F equals ma. Our acceleration is 1,000. Our slider that's hitting the dirt is 1 kilogram, or 1, and we get 1,000 newtons. So 1,000 divided by 40, we get 250 pounds. Hell yeah. So now we're getting 250 pounds, and if our slider is only 1 square inch, we're getting 250 pounds per square inch of pressure every time that slider, smacks the earth. And we'll do more about F equals ma. But yeah, it's as simple as that. Mass, is a number. Acceleration is in meters. Change in velocity is meters per second. And you get a force in newtons. Divide by 4, you get a force in pounds. And that rounds this one up. It got a little crazy at the end. But yeah, they're going to ask what's acceleration. And at the end of the day, you better at least have a very simple concept of like, whoa, well the other acceleration was half this time. So it went from 10 meters per second to 5 meters per second in half of 0.125. What's half of 0.125? Well, that's 0.625 seconds. So your change in velocity is 5 meters per second. And so this is the acceleration, is your change in velocity over change in t. So 5 divided by 0.0625. So 5 divided by 0.0625, and we get 80. So there you go, 80 meters per second. And that's literally, we considered it linear. So, no, we just kind of guessed that this 1/5 was pretty close. So anyway, so the acceleration from there to there was 80 meters per second. That means our guess from here to here, we know this acceleration has got to be higher. So I'm just going to say this was not a fifth. That gets you the fact that this acceleration goes to 8 meters per second right away, and this number should be higher. So this is probably 100 meters per second to where it goes from 10 to 8, because the time frame is going to be shorter. I don't know if you can see that, but it's not a linear scale. That's just saying this thing slows down linearly and speeds up linearly, but it doesn't. Because it's on a circle, we said that, hey, if this is way out here, a small change in the circle spinning is a huge velocity change. So the velocity change is not linear. It's secant squared. That's crazy. No one knows what secant squared is, but at least throwing some numbers at it, you can actually get to the answer without using secant squared. And then accelerations, you can get there without differentiating secant squared theta again. You know what I mean? So that's that, and we did good. I don't know if it was like half hour, 45 minutes, 1 hour to do this, but this was such a good one. I'll get better, and that's a video.